Hi everyone, and welcome back to our project, FIDELTA, FPGA-based Incremental DELaunay Triangulation Acceleration. In this video, we will examine the key performance indicators we're setting for the project, as well as the state-of-the-art of DELaunay triangulation construction in 2 dimensions. The key performance indicators we'll use to evaluate our results are correctness of the triangulation, time of construction, and ease of use. Even though in some situations an approximated solution could be enough, we want the triangulation found by our implementation to be exact. This is not naive, as we have to take into account several degenerate cases, like 3 points being collinear or a circle intersecting 4 of them, because when this occurs, the solution is not unique. As we'll see later, since it's an old problem in computational geometry, a lot of work has already been done to optimize the triangulation construction, especially in the simplest case, the offline bidimensional one. So, in order to achieve a significant speedup, we'll need to leverage on parallelization and optimize the implementation in order to fully exploit the potential of reconfigurable hardware. During tests, the overall execution time will be given by input-output, as read-write operation can sometimes take as much time as the triangulation itself, connectivity latency, since the FPGA is instantiated via cloud, and this will inevitably introduce some overhead, and of course the construction of the triangulation itself, which is the KPI we want to optimize. When used, this tool will almost always be integrated in higher-level applications, hence the need of an easily understandable and lightweight interface to facilitate end-user implementation. We'll now look at what is the state of the art in both research and already available solutions. The main approaches for the construction of the triangulation fall under 3 categories: divide and conquer, sweep line, and incremental. Introduced by Jubas and Storfi, the divide and conquer algorithm is pretty straightforward. We split recursively the map in 2 regions, build the sub-solutions, and then merge them together. The sweep line method, proposed by Fortune in 1986, provides a clever construction of the Voronoi diagram. It consists in sweeping a specific curve across the map. Thanks to some geometrical tricks, in the regions behind the curve, the Voronoi diagram will be correctly plotted. Since the DELaunay triangulation is the dual graph of the Voronoi diagram, it's easy to obtain it at this point. And in the end, the incremental method. We start by wrapping all the points in a big triangle. Then, one by one, we consider each point and see what triangles must be changed in order to have, at each step, a legal solution. Each of the 3 methods mentioned above can achieve the optimal time complexity of n log n. The divide and conquer is in practice the fastest, but its implementation can be tricky when it comes to parallelizing it. Fortune's algorithm is very elegant, but we think that the degree of parallelization reachable here would be quite shallow and focus more on lower-level operation optimization. The incremental is instead the one we'll implement. As proven by Belloc and others, with some modification we can achieve a high level of parallelization and a polylogarithmic iteration depth, while maintaining the algorithm simplicity. Let's now take a look at some existing alternatives. Triangle is a standalone implementation of the divide and conquer algorithm, and it's currently the fastest sequential solution available. While slower than Triangle, the DELaunay function available in MATLAB must be taken into account for being an accessible and ready-to-use tool. Coming then to available parallelized solution, the GPU-DT library performs an original method for the triangulation, exploiting CUDA technology provided by NVIDIA GPUs. In the end, Prakash and Miller developed an implementation based on MPI that fragments the workload by simply dividing the map into regions, assigning each of them to a separate CPU, and then merging the solutions. Given this landscape of heterogeneous possibilities, we think that there's still unexplored potential for new approaches, especially considering the benefits that reconfigurable hardware could bring. But we'll talk about that in the next video.